Dear students, welcome to the online class. I am Dr. S.S.C. Hiremat. In this video, you are going to study about the Debye Huckel Onsager Equation. We know strong electrolytes are completely ionized even in the moderate concentration. But the equivalent conductance of strong electrolytes increases with dilution. This effect was explained by Debye, Huckel and Onsager by using the two effects. Those effects are the relaxation effect and asymmetric effect. Now, let us discuss about the relaxation effect. When there is no potential, suppose this is one ion, positively charged ion, it is surrounded by oppositely charged ion symmetrically in all direction in this way. This is in the symmetric system. It is in symmetric. Means oppositely charged ions are surrounding this ion uniformly in all direction. But when the potential is applied, suppose this is negative potential, this is negative potential and this is positive electrode. This is negative electrode and this is positive electrode. Then what happens? Cations move towards cathode and anions begins to move towards anode. Then the symmetry gets disturbed. Then what happens? Okay, this is negative ion, another negative ion, negative ion, negative ion, negative ion. In this way, this is the symmetry. But cation is not at the center, but it moves to one side. It means when the potential is applied, this ion is surrounded by the oppositely charged ion and it is not symmetrically. Means more number of oppositely charged ions are in the opposite direction of the motion. Means cation is moving in this direction and more number of ions are in the opposite direction. Therefore, this movement of this ion is opposed by the oppositely charged ions which are dragging it back. This effect is called the asymmetric effect, or this is relaxation effect. Now, after some time, new ionic atmosphere is formed. Again, this stage is reached. Means this ion is surrounded by the oppositely charged ion symmetrically. This time is called the relaxation time. This is called the relaxation time. Means after some time a new atmosphere is formed and this ion is uniformly surrounded by the oppositely charged ions. This is called the relaxation time. Means once it becomes asymmetric and again it becomes symmetric, the time required for that is called the relaxation time. This was explained by Onsager in the year 1927, for which the equivalent conductance at infinite dilution increases with dilution. Then he gave one expression for the force. This opposing force is explained by, that is opposing force F. He gave one equation, that is epsilon cube Zi K small w capital W divided by 6 d k t, where epsilon is charge on an ion, means here in this case positive ion, we are thinking about that. Then Zi is the valency of the ion. Then small k, this is kappa, this is called the kappa, that is reciprocal of radius of ionic atmosphere, reciprocal of radius of ionic atmosphere, ionic atmosphere, which was derived in the Debye Huckel theory of strong electrolytes. Then W is the Z plus, it is defined by Z plus Z minus 2Q divided by 1 plus root Q. In this way W may be defined, which is related to the total charge of the atmosphere and valency of the cation and anion. Then D is equal to dielectric constant. D is dielectric constant. Then K is Boltzmann's constant. Then T is temperature in Kelvin. In this way, Onsager gave one equation for the force which is opposing the moment of the ion. Here, that is force is equal to epsilon Q Zi K W P D K T. This is about relaxation effect and asymmetric effect which opposes the moment of the ion and which depends upon the concentration. Suppose concentration is decreased, means opposing ion becomes less. In this way, the relaxation effect depends upon concentration of the ions. Now, the moment of the ion is opposed by another effect. That effect is called the electrophoretic effect. Suppose this is one electrolytic cell and this is negatively charged and this is positively charged, and one ion is moving towards the oppositely charged electrode and the ions surrounding it are moving in the opposite direction of this ion. Then there is a friction between the oppositely charged ions because this ion is moving in this direction and this ion is moving in this direction. In this way, when one ion is moving in this direction, the oppositely charged ions are moving in the opposite direction. At the same time, the medium or the solution is also moving in the oppositely charged opposite direction. Okay, thus the movement of this ion is opposed by the frictional force between the medium or the solvent and the oppositely charged ion. This effect is called the electrophoretic effect. This was studied by Debye and Huckel. It was studied by Debye and Huckel, and they gave one expression for the force, that is F is equal to that is K, small k, capital K, I, V, epsilon, Zi, 6 pi eta, 6 pi, where K is equal to the reciprocal of ionic radius of ionic atmosphere which was derived in the Debye Huckel theory of strong electrolytes. Then K, that is Ki, is the frictional force. This is called the frictional force. which opposes the movement of the ion, which opposes the movement of ions. Then V is the potential gradient, potential gradient, potential gradient, that is volt per centimeter, which may be taken as equal to 1 divided by 300 ESU, electrostatic units. Means 1 volt per centimeter is equal to 1 divided by 300 electrostatic unit. Then, as you know, E is the charge on the ion, charge of the ion or on the ion. Zi is the valency of the ion, and eta is the coefficient of viscosity of medium, This is about the expression for the electrophoretic force. This is electrophoretic force which opposes the movement of the ion. Thus, these are the two forces. Relaxation force. Relaxation force is equal to epsilon cube Zi K, then W capital V divided by 6 d K T. This is relaxation force. And another one is electrophoretic force. Electrophoretic force. It may be written as, that is kappa or K, and Ki, then V epsilon Zi divided by 6 pi eta. Then there is another force. When the ions are moving in one direction and oppositely charged ions are moving in the opposite direction, okay, thus there is a force that is also called the frictional force. Then the moment of the ion is, that is frictional force. Frictional force is equal to velocity of the ion or the linear velocity of the ion, and the proportionality constant is the frictional constant. This is another constant. Means it depends upon the velocity of the ion. Okay, here we have not mentioned the velocity, but here it depends upon the velocity of the ion. Thus, these are the three forces opposing the movement of the ion. Now, driving force. Driving force means these three forces opposing the movement of the ions. Suppose one ion is moving towards the right side. These forces opposing means these oppose the movement of the ion. But when the potential is applied, that potential is called the driving force. Driving force means applied force. Thus, the driving force is responsible for the movement of the ions against these forces. Then the driving force depends upon, that is this force, that is F, driving force, this is also F. It depends upon the charge of the ion, and another, that is valency of the ion, and potential gradient of the ion. Okay, now let us number these equations. Suppose this is equation 1, and this is equation 2, and this is equation 3, and this is equation 4. Means equation 4 gives the value of the driving force which is responsible for the movement of the ions. Thus, under steady state, under steady state, under steady state, driving force is equal to opposing forces. This is the driving force which is responsible for the movement of the ion, and these are the forces which are opposing its motion. Now we may write that is epsilon Zi V, that is the driving force under the steady state, means here there is a streamline movement of the ions, then which is equal to, that is the relaxation force, okay, that is relaxation force plus electrophoretic force, plus frictional force. Thus we may write here, this is driving force is equal to these forces. Then driving force is epsilon Zi V is equal to, let us take this frictional force first, that is Ki into velocity of the ion. Here Ui is the linear velocity of the ion. Here Ui is the linear velocity of the ion, okay, plus relaxation force, that is equal to epsilon Q Zi K small w capital V 6 D K T plus next one, that is K or kappa and Ki V epsilon Zi divided by 6 pi eta. Okay, now suppose this is equation 6. Divide equation 6 by Ki and rearrange. Then what happens when these are divided? Okay, we are going to get epsilon Zi V divided by Ki is equal to Ui plus epsilon square Z K W V divided by 6 K D K T, that is 6 D K T divided by Ki plus Ki gets cancelled. This K and this K gets cancelled, but let us write now K epsilon Zi divided by 6 pi eta and Ki. Okay, now let us rearrange this. On rearranging, we are going to get, let us take Ui this side. Ui is equal to, you take this side, that is epsilon Zi V divided by Ki. This term means this is taken left hand side, this is taken right hand side. Then terms become negative, that is minus epsilon cube z k w capital P divided by 6 d k t ki minus this ki get cancelled, then you are going to get k v epsilon zi divided by 6 pi eta 6 pi eta, that is ki gets cancelled, we are going to get this 6 pi eta. Then for infinite dilute solution, for infinite dilute solutions, that is k kappa is equal to 0, means the reciprocal of the ionic radius radius of ionic atmosphere becomes infinite for infinite dilute solution, and infinite difference equal to 0. Therefore, this third and fourth term disappear. Thus, third and fourth terms neglected. Then the equation becomes ui is equal to epsilon zi divided by this v equal to 300 and this is ki. But here, instead of using the ui, we are going to use it as the ui naught. That is equation 6, and this is equation 7, and this is equation 8, and this is equation 9. Here, for infinite dilute solution, ui is equal to ui naught, means it is taken as, in the moderate solutions it is taken as ui, in the infinite dilute solution it is taken as equal to ui naught. Okay, then we know the relation between equivalent conductance. Here ionic mobility is related to equivalent conductance, that is ionic conductance, related to ionic conductance as ionic mobility is related to the ionic conductance as ui is equal to lambda I divided by, or let us take ui naught equal to lambda I naught divided by f, where f is equal to Faraday's constant, which is equal to 96,500 coulombs. Then for moderate solution, this is equation 10. Suppose this is equation 10. Equation 10 becomes equation 10 becomes ui is equal to lambda I divided by alpha into f. Here, for the infinite dilute solution, its ionic mobility is equal to equivalent ionic conductance at infinite dilution, that is equivalent conductance at infinite dilution. This is not ionic conductance, this is equivalent conductance. Equivalent conductance. Here F is the Faraday. Then equivalent conductance depends upon the ionic mobility at the infinite dilution. In this way, here F is the constant. Whereas in the moderate concentration with the degree of dissociation alpha, and F is the Faraday's constant, and the ionic mobility is equal to lambda I, that is equivalent conductance at concentration C, at some concentration C, that particular ion. Okay, then this above equation becomes, what is that? Then equation, suppose this is 11. Okay, from equation this is 9, 10 and 11. 9, 10 and 11. The equation 8 becomes, this equation. What is ui? Okay, this is equation 8. ui equal to alpha not divided by alpha f. Sorry, lambda I divided by alpha into f. Okay, then this is equal to, that is ui naught equal to this term. Okay, that is v equal to 1 divided by 300. Then ui naught equal to this term equal to ui naught. Then ui naught equal to this term. Then this becomes lambda I naught divided by f. Lambda I naught divided by f. Okay, that is lambda I naught divided by f, and the remaining terms remain as it is. Okay, then let us rearrange this. This equation. Then this is equal to lambda I naught divided by f. Then for strong electrolytes, alpha is equal to 1. For strong electrolytes, alpha is approximately equal to 1. Then equation, suppose this is 10, 11, this equation 12. Then equation 12 becomes, this is equal to lambda I equal to lambda I naught, this is f. Okay, lambda I naught minus, then we may take here the 1 epsilon outside, and we may take 1 k as the common, Okay, then one k as a common, and phi also we can take, phi that is equal to phi may be taken as common. Then you are going to write epsilon, or let us write this term first, that is k phi epsilon is taken, k phi epsilon is taken. Then let us write this equation first, that becomes zi divided by 6 pi eta, 6 pi eta. Then minus of minus, this becomes plus into bracket, common bracket. Then and epsilon k phi is taken, epsilon square zi remains, and k is taken, phi is taken, only w is there, divided by 6 d k t and ki. Okay, ki. In this way we are going to get. Then let us rearrange this. This is equal to, and another term f is also there, this f common to all. Okay, common to all. Then we may write lambda I equal to lambda I naught minus f epsilon kappa divided by 300, and as you know, that is one kappa is there. Okay, this is sufficient. Then this is equal to, into bracket, zi divided by 6 pi eta, 6 pi eta. Then you may write 1 epsilon here and w here, then 6 d k t. Okay, and epsilon, 1 epsilon is taken, 1 epsilon zi ki, and this phi is taken, phi is common to both, and instead of this you may take here, this is equal to 300, this is equal to 300 as it is. Okay, then ki into 300 divided by 300, we may write in this way. Okay, we may write 300 multiplied by 300 divided by 300, and this becomes lambda I equal to lambda I naught minus f epsilon kappa divided by 300, then zi divided by 6 pi eta, then plus epsilon w divided by 6 d k t, and this is equal to, this is taken as equal to lambda naught divided into 300, and only 300 is there, lambda naught into 300. Okay, now the above equation may be written as, the above equation may be written as lambda I equal to lambda I naught minus f into epsilon divided by 300 into bracket zi divided by 6 pi eta plus epsilon w into lambda naught divided by 6 dkt into this k is taken from this, that is k. Suppose this is equation 13. Equation 13. We know from Debye Huckel theory of strong electrolytes, we know this K, we know that is copper or K equal to, this is copper or K is equal to 4 pi epsilon square divided by 1000 dkt and summation of Ci Zi square whole raised to half. Suppose this is equation 14. For univalent electrolyte ions or univalent ions Zi equal to, that is Z plus equal to Z minus equal to 1. Then summation of Ci Zi square is equal to C Z plus square C Z minus square. This is equal to C into bracket 1 plus 1, that is equal to 2C. Then summation of Ci Zi square raised to half equal to root 2 into root C. Then equation 14 becomes, then equation 14 becomes that is K or copper equal to 4 pi epsilon square divided by 1000 dkt divided by 1000 dkt and summation of Ci Zi square, that is equal to C raised to half into root 2 into root C. Then equation 13 becomes lambda I equal to lambda I naught minus F epsilon divided by 300 into bracket Zi divided by 6 pi eta plus epsilon W lambda naught divided by 6 dkt into, this is root 2, if you take inside that becomes 2 into 4 8 pi epsilon square divided by 1000 dkt, so this is outside, raised to half into root c. Now there is another 300 is there. Here also one 300 is there. 300 is there. Then we may write this equation as lambda I equal to lambda I naught minus this into this one term, that is f epsilon divided by 300 into this into zi divided by 6 pi eta, this is eta, into 8 pi epsilon square, 8 pi epsilon square divided by 1000 dkt raised to half. Okay, and another term plus another term, this into this, this is equal to f into epsilon divided by 300 into 300 epsilon w divided by 6 dkt. Now let us write lambda naught afterwards, that is outside. Then 8 pi epsilon square divided by 1000 dkt raised to half into lambda naught, these two terms over, and this is square bracket. Then we may write root c. Then we may write this totally one term is taken as equal to, this term is taken as equal to a, and this term is taken as equal to b. Okay, then we may write this is lambda I equal to lambda I naught minus a plus b lambda naught into bracket root c. Now let us number this equation as 14 and this equation as 15 and this final equation as 16. Okay, equation 16 is the Debye Huckel Onsager equation for the strong electrolytes, and it is applicable to a solution, and it is used for a solution. It may be written as lambda is equal to lambda naught minus a b lambda naught into bracket root c, that is 17, equation 17, where a and b are the constants and lambda is the equivalent conductance at concentration C at concentration C, and lambda naught is the equivalent conductance at infinite dilution. This is also lambda naught, equivalent conductance at infinite dilution. Thus, the equation 17 is the Debye Huckel Onsager equation, which is applicable to strong electrolytes. This is Debye Huckel Onsager equation applicable to strong electrolytes.